everyone again. So as I promised, we're going to go over all the different sorting algorithms. It's mainly going to be covered in chapter 22 of the book. Usually I like to cover this to see the, the developing of algorithms, as you can see, developing efficient algorithms, and you can see that in this sorting algorithms, and it's going to help you to understand, maybe hopefully help you for your algorithm class in the future and next semester, and so also it's good for our class to kind of see how we can improve our work, our code, by just think about it in a different way and solve same problem in a different way, and some of them are going to be better, more flexible than the others, or they're just going to have their own application, right? So there's always a trade-off, right? Sometimes we have to decide. So the execution time is basically, when you're running your code, you're trying to understand how fast your code is going to be or to work. And it's really hard to compare. Like if you're running the same exact code into different machine, depends on how much load is on the hardware of the machine or the system. They're going to have a different execution time. So when you're trying to see if an algorithm, for example, works fast enough, just by running it on two different machines and see how it's going to work and how fast the execution is going to be, it's not going to be a very reliable way to compare the algorithms with each other. And also, it also depends on the inputs, right? Sometimes some of the algorithms are going to be very sensitive to the type of input. Sometimes they're going to act really fast, and sometimes they're going to be very slow. Depends on what types of input, what type of data you're going to use. So we already see the example of the linear search. We're talk about the linear search algorithms and binary search algorithms, right? So the linear search is going to work order of n, but if we know that our data, the input data, is already sorted, then we don't really need to use a linear search, right? So no matter what, even if the list is sorted, linear search is always going to act order of n. But if we know it is sorted and we use binary search, then we're going to be a lot faster. Also, if we're researching, especially like when we're searching for an element, if the element is in the list in the beginning of the list, it's going to be a lot faster than if the element is going to be more in the end. So we have to kind of consider the average time, right? Sometimes in the algorithm situation, we even have to run it for maybe 10, 15 times and find the average time. And that is going to be the average of like how things work. So basically we have a best case scenarios, we have a worst case scenarios, and then we have like some average case scenario that we have to consider all of those. So based on like what we just explained, it's hard to basically measure the effectiveness of any algorithms based on their execution time, because as I said, the execution can be changed and depends on the inputs, depends on the hardware, and how much load is on the hardware. And so, in the theory, statisticians or mathematicians, they don't want to be dependent on basically a specific inputs and any specific, as hardware. So they want to be able to compare these algorithms with a completely different way that is not related to their basically those parameters. So how they come up with the comparing it, it's using the growth rate of them. So basically they use a growth rate. So the big O notation is what is basically going to be used. So the example of a linear search that we just explained, when you're searching this, again, we have to maybe run it 10, different times for a random inputs, right? Sometimes our random inputs, the key that we're looking for is in the beginning, sometimes so it's completely random. So if you just keep running this and then calculating what is happening, and we calculate the number of comparison, right? So it doesn't matter how fast it's going to be as far as the time, right? We're not looking at the execution time. We're looking for particular instructions that are going to be executed. And so when we were doing something like a search, the main thing that we have to do is doing to comparison, right? So we have to compare the key with each of the elements in the list. So we have to see like how many times we have to do this comparison at least. So and the number of the times that we have to do the comparison has nothing to do with the execution time, right? So it's just gonna tell us an estimate. So if you have more number of comparison, you're probably gonna have more time to finish it on the exact same machine, on the exact same inputs, right? So, but we still can compare two algorithms based on the number of the comparison, a number of a particular basically instruction on them. So if we just look at the number of comparison in average on linear search, we see that in average we're going to compare n over 2 times, right? So that's the number of comparisons that we have to do on average. And so again, average maybe 100 times you're running it with completely random inputs, and then you just keep checking the number of comparison, and then you feel like, okay, if I have 1,000, 10,000 elements one time, sometimes the number of comparison is 10,000, sometimes it's 2, sometimes it's 50, and sometimes 500. So you have to just kind of like average those numbers. So the results is come back as average of n over 2. And we know the worst case scenario, right? So if you have n element in your list, and n for us is like a really large number, right? So if you have n, it's not a constant number, it's a large number. If you have n numbers in your list, you have to do n time comparison, right? So it's a worst case scenario can happen. But here we're talking about even average case is going to be n over 2. Even the average scenarios is going to be order of n. And that means what? When we're talking about the order of magnitude of this is n, that means the growth rate of this algorithm is n. And that means that if you double size of this array, then you have to expect that the number of the comparison is also going to get doubled. And that's not a bad thing, right? So it's at least we know this is going to act linearly, and that's exactly going to be depends on the number of the elements in the list. So basically scientists they're using the big O notation or basically the abbreviation for order of magnitude is going to be the big O notation, and that's basically talking about the growth rate of an algorithm, so we can compare the algorithm. And so when algorithms are in order of n, then we're showing it with O, and that's going to be order of n, and we're going to pronounce it as order of n. And that is going to be our big O notation of growth. And that's telling me that if the order of a magnitude of an algorithm is n, that means this algorithm growth rate is going to be at a linear rate, which we know that linear search is actually going to do that. It's our order of n. We also know that in another algorithm, for example, binary search, the order of magnitude for that is order of n log n, right? And that means that the growth rate compared to number of elements or the size of this array is going to be the log n. That means if I even double size of this array, the number of the comparison is not going to be double. It's going to be log n. And so that means it's going to be a lot faster than what we have in a linear search. So binary search is going to be faster than linear search. So as just I basically explained, so best, worst, and average case scenarios are important for us, and we need to consider them to analyze the different basically algorithms. And so it's and specifically a worst case analysis is easier to understand, and also is more common because based on that we can see that worst case scenario, we're expecting worst case scenario what's going to happen to to our algorithm and to our basically to our execution. So that's why we're basically focusing on legal notation mainly, or basically, or in a worst case scenario. So here's some also comparison between the number of elements. Like, so you can see, like, we have 100 and 200. So this is the size or the number of elements, and then we're also talking about the order of a function. So a function n is n, means it's going to act like linearly as we're doubling size. So from 100 we'll go to 200. It still is going to be double. Even if we have an order of n2, still from 50 to 200, is still going to go over it twice, and so on and so forth. So as you can see, we're going to see that the growth is always going to be linearly happening, and that's exactly going to be the way that it's because it's basically order of n, right? So I'm sure you guys are familiar with this concept, and even in the high school. So I'm not going to talk about that too much. You may want to review the growth rate, and or maybe also I'm not going to go to the theoretical part of it because it's not really the job of our class. But I'm sure you're going to have more theory behind it somewhere else. So now, as I said, we're going to move now to, we already compared the linear and linear search, basically searching algorithms we know about binary and linear search. What we're going to do now is basically we're just trying to go over the sorting algorithms. So I want to focus on sorting algorithms, and the sorting algorithms are mainly going to be covered in the chapter 23. And so as we're going over these algorithms, we'd like to talk about I'm just now moved to the chapter 23, which is mainly talk about the sorting algorithm. So we'd like to talk about in sorting algorithms. We're going to talk about each of those algorithms, and then we're going to compare them with each other. We're going to compare them for based on different things, like if they're stable or not, and how fast they're going to grow, right? So their order of complexity for maybe best and worst case scenarios, mainly order big O notation specifically. And we're also trying to compare them and see if when it's better to use which of those algorithms. So some of them you may think, okay, who's going to use this? And then we're going to talk about the fact that actually they have a lot of applications. And so it's going to really demonstrate the performance of the algorithms and how we can improve them, or how we basically can go from one algorithm to another, how using loops and particular techniques are going to change a performance of an algorithm, and so why we have to kind of maybe even avoid it or do other way to handle that, so our program going to be more efficient and have a better performance. So that's why we based study sorting algorithms mainly. Now the question maybe, what is sorting algorithm? Why we need to sort? And we all know that when we have data, sometimes we have a lot of integers or double value or even characters, or even the other types of objects. Right? And we like to be able to order them in a way that we can understand them even better, right? So be able to sorting the data it's important, right? So the Java API itself providing this um, sorting methods that you can just basically call those methods and use them and sort your list, or basically data structure that you have that you want to sort. One of this sorting algorithm is available on the arrays, and the other one is available in collections. So both of them are in Java util. So collections and arrays, and you can see that they both use the class. That means most likely most of the methods in those classes, even the sort method, are going to be the static methods. So you have to say just Java util arrays, and then you can just say dot, and you have access to the sort algorithm. So we can, when we have data, we like to sort them. So here, when we are going over these sorting algorithms, the definition for the book is that those algorithms, those arrays of data that we're trying to sort, they are integers. So it make it easier for as far as the illustration and explanation.